Hi, so this is the first physics video tutorial for Chapter 9, which involves statics, and we're also going to look at one arch problem in the second video, but this video shouldn't be too long. So the first video, we're going to look at a couple problems. The first problem has a mass that's being suspended, so like you can see the walls in this situation are kind of running in this manner. So we have a mass that's being suspended. You could think of it as, I don't know, some kind of light fixture like a chandelier or anything else that's hanging from two wires. So you have two wires that's attached to the wall up here at this point, and it's attached horizontally over at this point, and together they're holding up this mass. Okay, so apparently the mass is 200 kilograms, and we're going to use equilibrium to figure this out. So first, note, since it's in equilibrium, we know that the sum of the forces in all x, y, and z directions are 0, and that the sum of the torques are 0. So we'll just apply one of those at a time and see what we get out of it. Okay? So in the y direction, the sum of the forces is 0. So let's think, in the y direction, this guy is completely horizontal, so he doesn't have any y component. The guy that's going straight down for gravity definitely does. So in other words, that's mg. So mg is going down. So we'll take down to be, I guess down will be negative. So we'll make up be positive. So it's going to be minus mg. So you know what? I'm gonna put minus mg. So what is going up? Don't we have part of this vector that's going up? I think we do. Just the y component of that vector. So if that's 60, then that means this guy is 30. And we can kind of use whichever one we want. So we could go the cosine of 30 or the sine of 60. You know what? I'm going to go cosine of 30. I like thinking about it from this perspective. So cosine of 30 is that component, the vertical component. So anyway, whatever that force is, we called that one A. So A, the cosine of 30 part of that, or the sine of 60, whichever one you'd like, is what's in the y direction, and then we said gravity is going down, so minus mg, and since it's not moving, since it's in equilibrium, those forces add to 0. So now we can solve for Fa. So in other words, the force, the magnitude of the A force total is going to be mg divided by the cosine of 30 degrees. So the mass was 200 times 9.8 over cosine, oh my gosh, that's a C, cosine of 30. I'm going to put that in my calculator and see what I get. Sure, it's in degree mode. So if I do my significant figures, well, first I'll just tell you I got 263.213. It's a force, so it's newtons. Significant figures, how many significant figures? 200 kilograms. We'll say that it was exactly that much, so we've got 3 significant figures then, so that's 2260. Ooh, getting sloppy today, I'll have to watch that. Anyway, so that's the force A, so we've got that one. They also wanted the B force, so how do we do that? So I said, well, let's just try summing the forces in the x direction. We don't really have a z direction in this situation, and we could think about torques, but let's just try x first. So if we go the x direction, we've got B in the positive, so we'll say that this is positive, just like this was positive before, just the coordinate system that you're used to. So in the x direction, what have we got? We've got B. So from this guy, we've got B. It's completely in that x direction. And then we've got the x component of this guy. So that's going to be the cosine of 60, isn't it? Or in other words, it's like, if you look at it like this, it's the sine of 30. So I'm going to go sine of 30. Up to you, though. So minus that, because that's going in the opposite direction. It's going this way, right? So minus A's force, which we now know, but now we've got it times the sine of 30, or cosine of 60. Sum that and say it's equal to 0 because we're in equilibrium. And now we say that B is just going to be 2260 times the sine of 30 degrees. Which is what? I got 1130. Sine of 30 degrees, if you remember, is half, so it's half. And newtons, and there we go. Let's look at another problem. Okay, let's also consider a problem of like mechanical advantage, okay? So let's imagine that we're a person standing out here over in this location, and we're pushing down on a lever, and we're trying to move this rock over here, and we've got a little fulcrum stone, just a little guy. I kind of exaggerated how big it was. And we're trying to, here I'll try to draw a better job of the person. We're trying to budge that big rock, which is pretty powerful. Okay, so we're exerting this force downwards, and we're trying to overcome the mg over here by positioning that fulcrum stone. So what I think is important that you understand is that if we make r bigger by a fairly significant amount or move the stone, that's how we have control here. Okay? So in our book it says the small rock acts as the fulcrum. The force required at the long end can be quite a bit smaller since it is the torques that balance in the rotation about the fulcrum. So the idea here is that the torques sum to 0. So this is one of those situations where you're thinking about in equilibrium the torques summing to 0. So what are those two torques? So we're going to put those two torques into this problem and solve them. So let's see. So in order to actually make the rock move, we've got to accomplish that the torque over here is the same as the torque over here in order for it to just start to move. So we're just going to set those equal to begin with. So what are those two torques? So we're going to say mg times the small r, that's the distance between the rock and the fulcrum. We're going to set that equal to the force that we're exerting over on the other side, and that's going to be times big R. So what I thought you might do then is rearrange the terms. So if you rearrange the terms, I mean, you can kind of do it however you want. You can see that you're going to get this expression over here. And the idea is that this guy right here, if you flip it and you go big R over small r, that's your mechanical advantage. So you don't have control over the amount of force necessarily that you can push down. I mean, you have a certain maximum according to how strong you are, and you don't have control over how heavy the thing you're trying to move is, but you do have control over this ratio. So if you make large r and small r and you mess with those, you can accomplish moving this rock and exerting a greater mechanical advantage. Okay, so I wanted you in the reading guide to examine exercise B, which says that it basically asks you to include the angular term. So notice, when we looked at this, we were kind of ignoring the fact that mg is not really perpendicular to the radius of motion here, is it? And neither is the force we're pushing at. So it says, if you included that angle in there and you included angles on these parts, would it still work the same way? And I think the answer is yes. So let me give you just a little bit of an idea of how you might do that. So I'll get you started on that problem and then you can finish it. So if we go like this and we look at that axis, we had mg going straight down, right? And so same thing with our pushing force over here. Just draw the little triangles and dissect it according to angles. So remember, if you're looking at torque, the part that's actually torque is only the perpendicular component. So let's try to draw the perpendicular components here. So over here I kind of have a triangle, don't I? I have the red part, I have the purple part, and then let's just let's just close this in over here. So there's the angle, yes? So this red part is what the rock is, what's happening to the rock according to gravity. And the purple part is the true thing that we want. That's the lever arm, the true lever arm. So let's just put an X on there. That's what we're truly trying to find. Yeah. So if we solve for that purple part, don't we get that that is... I kind of drew this badly. Let me fix it. So let's just start over. So let's see. So that kind of looks like it's off to the side, right? But that's really going like straight down. So there's mg. And then we have this guy going perpendicular to the lever arm axis. So it's over there. And then this guy is like that. So there's the right angle. And we were investigating this theta up here, because that's the true theta away. So I'm going to solve this for x. So you can see that that's really just a cosine ratio, right? So you can go mg times the cosine of theta equals x. And then you can do the same kind of thing over here if you put a theta in there. And you can have that, for over here, you can have that the force push times cosine of theta, that's a p, equals, I don't know, let's call this y, because that's the true perpendicular distance that we need for our torque. So now if you set those equal, what do you notice? There's the answer in your reading guide. Okay, let's look at one more problem. Let's look at one more problem. So in our third problem, we're going to have a seesaw. So we've got a seesaw, and we've got two children or two adults. You know, adults like to have fun with seesaws too sometimes. And they are positioned at different distances. So the first adult, let's say that that adult weighs 30 kilograms. That's a light adult. Maybe I better say it's a child. And the second adult weighs a little bit less, 25 kilograms. So in order for that seesaw to stay balanced and not be moving, be in equilibrium, in other words, how far away does that second person have to sit from the fulcrum of the seesaw? So we're going to say the first person is 2.5 meters away. Okay, so that's like what? I don't know, 8 feet or something. Anyway, so what might help us? So I said first, you know, let's just try the sum of the forces in the y direction. So what forces do we have here? We have the force exerted by gravity over here. So that's like ma g. We have the force exerted by gravity over here, which is that person's mass times g. That's an m. And then at the fulcrum, we have like the board, or whatever you might say, like the metal from the seesaw, whatever it is. It has a certain mass, and it's also going down. We'll just call its mass big M. It's also being influenced by gravity, but yet then it's also, the fulcrum is also pushing back up with some kind of normal force. So we've really got 4 forces in our free body diagram, okay? So I said, well, let's just look at the y components first. If it's truly not moving and it's in equilibrium, then the sum of the forces has to be 0 in that direction. So I said Fn minus equals 0. So we know the mass is here. We know what gravity is. We could measure how much the seesaw weighs and get big M. So we could calculate the normal force that way. But our real question is, we're trying to solve for x in this case. We're trying to say, how far away does that person have to sit? So notice, x didn't pop up there. The real question is, how far do they have to sit from the fulcrum so that it doesn't move, the seesaw doesn't move? So there's no x there, so that didn't work. So you might try the sum of the forces in the x direction, but if you look at the vectors here, I don't think that would be very interesting. So I said, well, you know what, let's just try the torques. The torques have to sum to 0. So I said, okay, let's do that. So if we look at this guy, the torque is that distance, 2.5 times the force mag. And then if we look over here, isn't this guy going to be, isn't he going to be, or she, whoever it is, going to be torquing in the opposite direction? So, because the x is like opposite. So the real reason this is minus is because these two x's are opposite. So they're both like pushing down in this direction, but you might notice that like the x is really what's opposite. So this part and this we could have put like plus a negative right here. That would be what makes that negative sneak in there, okay? So if you're confused about that, that's where it came in. But anyway, so it's negative. And then, so that's the torque for the two people. Do we have any torques for the fulcrum spot, the part in the middle? And I think the answer is no, because there's no lever arm, right? Like there's no distance out for them to accomplish that kind of torque this way or that kind of torque this way. So those both go away. And what we have left is something that has x in it. Look at that. So now we can find x. So don't we know all these other things? So we could say that, I don't know, MA G times 2.5 equals MBG times X. The G's cancel too. And we get X is just that distance 2.5 times that mass, we called it 30. Yeah, that anorexic adult or child divided by the other mass. And we get, let's see, holy cow, that is really sloppy, but 2.5 times 30 divided by 25, and we get 25. What? Huh. 2.5 times 30 divided by 25. Ah, get 3. So 3 meters. So that person would have to sit 3 meters away since they weigh a little bit different for the seesaw not to move. Okay, so we'll have one more video after this and get a little more in depth on that one. Bye.